Finding my pen. So the thing about this is you get this right when you focus on, would we say, how do you describe a function? How do you, if you want to understand a function, what should you focus on? Yeah, the independent and dependent variables. What's the independent variable for this function being asked about? Time. Since. Okay. Time since started moving, and the dependent is? Okay, the height of the caterpillar. And so, right, so you can make that proper conclusion if you're focusing on the variables, right? Rather than this graph, which is not, which you all picked up on, is not a depiction of that function, right? What is this a depiction of? It's trail. So if you can't, what variables like would this be?
It would be like his horizontal vertical position.
Yeah, so like height is vertical position as a quote unquote function of horizontal position. Is height a function of horizontal position? No, right? That's what you were arguing, Lydia. That at a horizontal position, there's many heights. At some horizontal positions, there's more than one height that the caterpillar attained. But you can't be at one moment in time, you can't be at more than one height, right? At one moment in time, you can only be at one height. Okay, so yes, this is a function. But so the conclusion is no, this is not a function. Okay, so I contend that we can have a framework for which that curve is a function. How could that curve, so you already know? You already think you know?
Yeah.
So listen, I'll let other people think. So we'll hold on to your thought. So yes, height is a function of time since we started moving. Then we kind of said, nah, this isn't a function. But I'm going to say that I contend that could be a function. How could that set of points from A to B be a function? Winston has an idea. Any other ideas? How could that be a function? What's that? R3. Okay. What would your? Okay. Any ideas?
I would think something along the lines of like how many times, or you could take into account how many times like the caterpillar was at, say like height 3 or height 4 or whichever height, but I wouldn't know what you necessarily use as your independent variable.
Okay. So I want this set of points. I say that this set of points could still be a function somehow. How could this set of points be a function? Do you have any ideas? What's that? Okay. So you're saying the input is the horizontal position. Winston, what were you thinking?
I was thinking about a function that has an input of height above the ground and the vertical, and an input value of time, and it outputs the height as a variable and the ground as a different variable.
So independent is time, same independent variable as this one, time since the caterpillar started walking. And then what, so what is the dependent thing here? That would be depicted by that path, right? So what would the dependent thing be that's depicted by this path? At any given time, the caterpillar has just one what?
Position.
Yeah, because these points are like places on the wall, right? This is like position on the wall. So at any given time, the caterpillar has a particular position on the wall. Now, how do we describe that position?
How far, like in this case, how far to the right you are, and how high above the ground.
It's two things, right? Yeah.
Yeah.
So that position is then made up of two variables, horizontal and vertical position. So do you see that that's a function then? So for given any particular time, could only indicate one point on that curve, and that point would be represented as 2 in two variables. So what is that like? So our independent is t, and our dependent is so the function that has that curve is where the independent variable is t, and then the dependent thing is actually an ordered pair, an x and a y coordinate, a horizontal and a vertical position. So what kind of function is that? Do you know what kind of function that is? So it's like our xy. So maybe our x is one function of t, and y is another function of t. So given a t, that generates a particular point, or ordered pair. What that's called? And that's a composite. No, that's different. That's a composition because we still only got one thing out, right? So that here you put in a value and you get a correspondence point, 2 points, two values taken together for every one of these. So, yeah. So this is a parametric function, right? This is what we mean by a parametric function. So t is the parameter. And that parameter, then, for every one value of the parameter, you get an ordered pair, or it could be an ordered triple, or something like that. So that curve is a function, if you think of it as a parametric function of time. Right? A parametric function of time. Every ordered pair. For every given time, there's only one place the caterpillar could have been. So it's a function. But how is it not a function? One more time. How is it not a function, that curve?
Well, I'd say because there's multiple heights for a given time. If you were to look at like x has
multiple heights for a given time? No, that's what we said was a function to start with, right?
Yeah.
So how is this curve not a function? Multiple heights for a given what?
for a given time.
No. No. Height is a function of time. There's only one height for every time, but there's multiple heights. What? There's multiple heights for every or for some. There's at least, there's some multiple. Sometimes there's multiple heights for a given. So what is this quantity? What's the independent variable? Ground isn't a variable. The ground is that's an object. So what is this quantity?
Would it be X?
And what does it represent in the situation?
How far to the right you are?
Yes, right. Horizontal position or distance from the wall, right? So like horizontal position or distance from the wall. So height is not a function of horizontal position or distance from the wall or how far over you are. But height is a function of time, and each of these points could be a function of time, right? And that's where we come into a parametric function. All right, so let me show you some examples of parametric functions. So in terms of, so where do you see the graph of, where is t? Where's t graphed here? Right, it's behind the scenes, right? So the parameter, the independent variable, then doesn't show up on the graph. The graph is just the set of ordered pairs, which are all the dependent thing, right? So you don't show the independent variable on the graph. It's behind the scenes. So because of that, that opens up a door for lots of different graphs that. This one. So we can get all kinds of things that we didn't consider functions before, but now are functions because a function of a parameter, right? So that is a function, right? Here's the function. X is sine of t plus sine t, and y is cosine of t plus cosine t. So this is GC graphing that parametric function. It's a fun one here. So complicated function or not? So complicated? Well, x is t plus sine 2t and y is t plus sine 3t. It's not that complicated, right? What's that?
It's still like kind of complicated.
Well, I mean, the result, I mean, if I showed you that picture when you walked in today, you'd be like, what the heck is that, right? So then we don't see functions like that because it's not what we think of as a function because it's violating this vertical line test. But it is a relatively simple function. It's t plus sine 2t and t plus sine 3t for x and for y. Here's something a little more complicated. Not much, but a little bit. Cosine t and sine of t plus 5t. Okay, it's a function. If you have the right perspective, right? If you have the right orientation towards what you're looking at, that is a function. It's a function. Points on the graph are a function of parameter t. What else do I got here? How about this? Is it a function? Tell me how it's a function. How is it a function?
You can pass a vertical line test for one, but.
So then, if that's true, so how is it a function? If it passes the vertical line test, how is it a function?
that means that each,
Go ahead.
well, for each designated x value, there's one y value.
Okay. Right. For every y, for every x, there's only one y. Okay. How else is it a function? Yeah. What? Okay. Right. So ordered. So what we say is ordered pairs x and y are a function of parameter t, right? According to this. So since y is also a function of x, just visually we can see y is a function of x. Can we come up with that function? So here's this: the x of t is 1 plus 3t. Y of t 2 minus t squared. So can we come up with y as a function of x? According to the picture, we should be able to, right? How would we do that? Can we get a formula or a rule of x that gives us the y value every time and gives us just one y value for every x? Okay. Yeah. Right. Okay. So yeah. So if x is 1 plus 3t, then t is x minus 1 all over 3. And then, right. So then y is? So this set of points, y is a function of x, and also, according to that, but then also ordered pairs are a function of t. So is that what I have there? So if I graph both at the same time, they're right on top, same points, right? Same points. Okay, so this is the idea behind parametric functions, and so like we saw, it kind of opens up a whole new category of things that we didn't consider functions before in terms of graphs in the plane, right? And consider graphs of x and y. Now things that don't pass the vertical line test can be possible functions as well. Okay, so what about the circle of radius 1? Circle of radius 1. Is it a function or not? Circle centered at the origin of radius 1. Is it a function? Yes or no? Is it just yes?
I would say, yes, because you could use that radius and then you could graph all the points, or the coordinates basically, along to make that circle.
Okay, but when I'm asking if something's a function or not, then you have to talk in terms of what? What do you talk in terms of? Tell me it's a function or not. Independent and dependent. So you're saying yes. So then, what's the independent? What's the dependent variables? If it is a function.
So I'd say independent variable would be your radius.
The radius.
Yes. And okay. Dependent would be position or the coordinates of the circle, or that make up the circle.
Okay. So different values of different radii give different points in the circle. So for a radii, we get this point, and for another radii, we get this point. Is that what you're saying?
Yes.
So what's the radius here? What's the radius here? What's that? 1. So when r equals 1, which point do I get? Do I get all the points? Or do I get a particular point?
You get all the points.
Well, then that's not a function. So how do we think of a circle as a function? Is a circle a function? And if so, what are the variables that make a circle a function? So yeah, for instance, like the circle, x squared plus y squared equals 1. Is that circle a function? And if so, justify your answer. What do you think? Okay. So angle measure is independent, and then dependent is coordinates, x, y. Can that, for any given angle measure, is there only one coordinate pair on the circle?
If you define the radius, to be specific.
Yeah, okay. For a given radius, right? So for a given radius. Okay, so let's do it. So I wanna graph this as a function. So what about y as a function of x? Is y as a function of x for a circle? No, right? So what about just the top half of the circle? Is y a function of x? Yeah, right? So the top half of the circle we could write as y as a function of x. But I want to write the whole circle as a function. So in GC, I'm going to do control 2. Have we seen that yet? And then equals another control 2. And then I'm going to put my what my x is as a function of t, what my y is as a function of t. Okay, so what should I put? What's that? Okay, what do you get when you solve for y? Okay, so the circle is a function, y is a function of x? What will that give? What's that? The top half. So it'll only give the top half. So that the top half is a function. But I want to write the whole circle as a function. How can I write the whole circle as a function?
Would you use, for x, you'd use cosine, and then y, you'd use sine.
Cosine of what?
Cosine of the angle measure.
Okay. So the angle measure becomes our parameter, right? So I'm going to say t. It doesn't, you know. There we go. GC doesn't know, so lowercase t is built in as a parameter for parametric functions in GC. So lowercase t is not a free variable like, you know, A, B, capital letters. T is reserved for the parameter in parametric functions. So I can use a lowercase t. In this case, if I do cosine t, then it's meaning angle measure, right? Okay, and then y is sine t. Let's make it what should I do? Purple. Hold on a second here. I gotta change something. Let's do this. Okay, what happened? Thought we were going to get the whole circle.
I think it's only graphing, because that's just I would think it's that's the radius length.
Okay.
Or a radian worth.
1 radian worth?
Yeah.
Okay. So why did it do that? Why don't it just give us the whole circle?
Would we have to multiply by our radius on the cosine sine t?
What will that do to the x and y coordinates if we multiply by the radius? So like
it would establish that our radius is, or
So did anyone notice what happened over here when I hit graph? See this? What is that saying? Yeah, it's saying that t is from 0 to 1. So if I want to show the whole circle, what do I need t to be? 2 pi, right? So it's only showing what you said, 1 radian worth, which is 1 radius length. It was just showing, because t was only from 0 to 2 pi. So t in GC acts as a kind of, it's like a spray of all those values. So when t takes on all the values from 0 to 2 pi, it's going to graph all those points. All those points, cosine, sine, for every t value from 0 to 2 pi. But actually not, right? It's gonna do a discrete number of them and connect the dots, like we've talked about before. Okay. Okay, but you know, what if I want to graph something else? Say I want to use t now, and I want to graph. You know, I only want a quarter of a circle. So I wanna do something else here. So I want to copy. And then this will have radius of, if I want that to have 1.5 radius, I can just multiply the x and y coordinates by 1.5, right? Make that first one blue, this one red. So how much of this the red circle is going to show? All of it, right? So it's still going to be t from 0 to 2 pi. Well, what if I want to use t as my parameter, but I only want to show a quarter of the red circle, and I want to show all of the blue circle. I only want to show the first quadrant of the red circle. But I need to use t as the parameter for both. What can I do? How can I do this?
wouldn't you just limit your t to go to from 0 to pi over 2?
Okay. Now I show a quarter of both. I want to show the whole blue circle and a quarter of the red circle. Divide by pi over 2? Yeah, I want to keep the whole blue one and just a quarter of the red one. So what do I need to change? What to make this work? What do I need to change? Am I going to be changing the range of t? Every time I change the range of t, it's just going to affect both of them, right? So that being said, what I'd really like, say I'm going to have even more graphs. I want t to always go from 0 to 1. And now what am I going to adjust in order to get the whole blue circle and then just a quarter of the red circle? What do I need to adjust now? You got to adjust the functions, right? So how do I adjust this first function? I want to show the whole circle.
Wouldn't you just do t times pi, or no, 2 pi?
Inside the argument here?
Yes, to get the full circle.
You want 2 pi?
Yeah.
And here too?
Yes.
What do you think? Got it. Okay, and then what about the other one?
Would you just, since it worked with the last one, I'm assuming doing just multiply that one by pi over 2.
So this is, and then if I want to put more graphs on the same axes, I can always adjust the function so that t is always going from 0 to 1. And then I can just adjust my functions accordingly. So what did we really do? We said as t goes from 0 to 1, we wanted what? The argument to do what? That's what we call the argument. This is the angle measure going into cosine. We wanted the argument to go from 0 to 2 pi. And this argument we wanted to go from 0 to pi over 2. Does that sound familiar? Have you done anything like that before? We'll come back to that question. Okay, so that's familiar? Okay, so one thing in your homework that you'll have for this so I'm going to turn this one off. So I've got this circle right here. Is it a circle?
Yes.
Circles are supposed to be symmetric and round. Symmetric all ways, right? You just stretched it. It's still a circle though? Prove it. You prove that it's a circle? So it doesn't look like a circle to me. If you walked into the room today and asked you if that was a circle, you'd all say no. Right? What's that? So because this distance is 1 and this distance is 1, that makes it a circle? True for every angle. Okay, so how would we prove? So that means what we have to do, take any point on the circle, right? What are the coordinates of that point? No, this is any point on the circle, right? So what are the coordinates of that? And? And so we want to prove so in order to prove that, so have you done proofs? Want WTS to do WTS, know what that means? Want to show, okay? What do we want to show to prove this? WTS, want to show. So we're going to prove, we need to prove the blue curve is a circle. So to do that, we want to show what? So we got our arbitrary point. That represents every point on the circle. So we want to show, what do we want to show?
The coordinates match up to this formula.
No, that's given. We know that. That's where the blue curve comes from. The blue curve comes from the fact that x is cosine 2 pi t and y is sine 2 pi t. So to prove that curve now is a circle, what do we want to show? No, that might be how we do it. How we do it. What is it that we're wanting to show? Right, so it's a constant, right? So we want to show that the distance from the center to xy is a constant, the radius, right? So if we can do that, if we can show that the distance from the origin to that point xy is a constant value, and we do that by making that, letting that point be any point, right? So this represents any point. Then we've shown it's a circle. So what's the proof going to be? So here's the proof. We want to show the distance from the origin to that point is constant. So what are we going to do? So this is maybe what you were getting at. Okay, yep. And when you do that, so what is it you're finding? Like when you okay, so distance, right? So the distance equals? What's that? So distance to the origin, right? Distance to the origin. Tell me, what's up? Yeah, what? What's that? So then what distance to the origin is, you can use the distance formula from 0, 0 to the point xy. And we want to show that that distance is constant. In this case, the distance is? We just show that it's 1, right? So you finish. I think that's part of your homework. What's that? You finish. You're gonna finish it. So that's part of your homework, but that's a start. Okay, so now what if I really want an ellipse? I'm going to go back to what if I really want an ellipse, say that has that looks like, when the axes are to scale, looks like the curve that I just showed. And I really want an ellipse now. What am I going to do? How do I change the function to show an actual ellipse? So if I make the x-coordinates if I scale the x-coordinates, like if I magnify them, then that will change it. So what do I want to do? 2.5? Is it a circle? No, it's not a circle. Is it an ellipse? Prove it. How are you going to prove it's an ellipse? All the distances are the same to the center? Is the distance always the same? Constantly changing, right? Here it's 2.5, and it's decreasing to 1, and then increasing back out to 2.5. The distance to the origin decreases the distance to 1, etc. So it's different proof, right? It's different proof. But same kind of idea, that you have to, you know what the coordinate of a typical point is. What's the coordinates of this point? So now you're not, to prove this, you're not showing that that point is a constant value away from the origin. You're doing something different now. Okay, so that's also in your homework. So just by looking at it, so we can look at it and say, oh, it looks like an ellipse, but we're really just because it, you know, it has different radii at the x and y axis doesn't necessarily mean it's an ellipse, right? There's many curves that could go through those 4 points, right? There's many oblong closed curves that could go through these 4 points that are not ellipses. So the question is, how do you prove that that truly is an ellipse? Right? How do you prove that's an ellipse? That's something for you to think about, part of your homework. Okay, so back to our circle. Okay, so we talked about graphing the whole circle. Even when t goes from 0 to 1. Okay, so I want you, with t going from 0 to 1, I want you to write what the functions would be if you got GC. You can pull GC out. I want you to recreate this in GC. Or if you don't have GC, you can just write it down on paper. But what math lines should I put in to show this? And I want t staying from 0 to 1. So what angles are these two angles for the start and end of the red arc? Was it? 5 pi over 4 and 7 pi over 4. So what are we trying to do? We're trying as t goes from 0 to 1. What do we want? Theta to go from? So here's where we return to that conversation. As t goes from 0 to 1, theta goes from 5 pi over 4 to 7 pi over 4. Have anything? Have any to help you with that? Okay, so yes, you got it. I also want you to think about something that we've done about regarding this. Do you remember this? T goes from 0 to 1, theta goes from 5 pi over 4 to 7 pi over 4. Does anybody remember something like that?
Like the morphing?
Yeah, right. This is the morphing operator, right? So can you do it using the morphing operator? Because if you can do it using the morphing operator, you can just keep using the same morphing operator over and over again. You don't have to kind of figure out each one separately. You can just keep applying the morphing operator. Do you remember what it was? So we need what? We need 0 to give 5 pi over 4. That's right. So can you reconstruct it? Do you remember what it was? And then the morphing, so then if you use t, then it'll give all the corresponding values in between, right? So for every value in between 0 and 1, we'll give all the corresponding angles in between, right? So that expression for your angle measure, can you do it? Remember what it was? So when you plug 0 into it, it'll give 5 pi over 4. When you plug 1 into it, it gives 7 pi over 4. That's right. That's right. Okay, so let's do it again. Let's add some more to this here. It really looks like a face. That's incredible. Wow. Okay, go. Now those are parametric. Those are graphed as parametric functions using t from 0 to 1. Okay, so can you graph those as parametric functions 0 to 1? Fast, because the best part's yet to come. See if you can crank that out. So practice what you learned, right? Practice what you learned. And do it as a parametric function. As t goes from 0 to 1, you want what? You do it. Okay, so we're using the morphing operator, but these examples kind of you could figure it out without using that. So now we want to really put it to work. Okay, so now we want to do something where we really need the morphing operator because we wouldn't have any other way to do it. Are we good on the eyes? Okay, so keep working on that. So let's really necessitate using the morphing operator here. There we go. So we're going to do that. Is it a function? Is that curve a function? Yeah. How is it a function? Points, ordered pairs are a function of t, right? We're going to do ordered pairs as a function of t. So here's the deal. This is based on a circle. This circle. Let's see if I can get this here. Right about here. Okay. So this curve that I made for the tongue is based on a circle with center. What is that? 0.25 and negative 0.95. Okay. And radius, yikes, what's the radius? No. Oh, I think the radius, is it 0.5? Yeah, I think it's 0.5. Okay, so I'm thinking about the circle with center 0.25, negative 0.95, and radius of 0.5. So the great thing about parametric functions is we parse out x and y, right? So we think about what x does and what y does, right? So here's going to be our starting point for t equals 0. And here's going to be our ending point for t equals 1, okay? And so we can think of x and y separately and make progress on both of those separately. So let's do y first. What does y do as t goes from 0 to 1? And that purple curve, what does just the y coordinate do? What does it do? It goes down to this, right, so it's like at the center line. It goes down to the bottom and back to the center line. That's what y does. So you can work on just y. So what angle measures are that? Y going from center line down to the bottom, back to the center. Do you see that? If I was looking from here, all y does is go down to the bottom, back to the center line. So what angle measure is that? What about x? What does x do? As t goes from 0 to 1. So now look from the top. What does x do? Right. X goes all the way out to the right side and then back to the center. Right? So it's starting at the far left. It goes all the way out to the right and back to the center. So now your x and y are traversing a different angle interval, range of angles. But that's no problem because we're handling x and y separately in a parametric function. And we've got the morphing operator. Okay, so now we've got for the circle, whose center is that and whose radius is 0.5. We need y to do what? Start here at the left side, go down to the bottom. Sorry. Y to start in the middle, go down to the bottom, back to the middle. So what angle range is that? What angle range is that y is doing? So should we draw the whole circle? Maybe will that help? We'll draw the whole circle. So what does y do relative to that circle? So that's thinking about the angle measure that y goes through. And what does x do? Just looking at the horizontal position in terms of angle measure. You see what I'm getting at there? So we've got two things going on. We've got to move the circle from 0, 0. We've got to get a set circle that's centered at 0.25, negative 0.95, radius 0.5. What's that? What does x do? So where does x start? At t equals 0. Where is it on the circle? X. Right, the far left side, right? X starts at the far left. And then what does x do as t goes from 0 to 1? It goes all the way to the right. See, it makes it all the way to the right here, and then back to the center. So what angle range is that?